2 hydrates and others, what are for the occurrence of hydrates with different inclusion compounds and materials. The next aspect is just kind of the history, and keep in mind that hydrates have been known as a chemical curiosity back to the 1800s. The first real studies of gas hydrates were more in pipeline studies, and still today of looking at the plugging of gas in pipelines and others. The first theoretical occurrence or the suggestion that hydrates may occur in nature, particularly in permafrost environments, was by Yuri Makagan, which still is a good friend. He actually lives here in the US, in Texas at Texas A&M. And hydrate recovered cores for the first time in Alaska in 1972. Kind of obscure programs that most people haven't seen in the past. There were industrial programs by companies like Arco and Exxon and others, and similar projects in the Mackenzie Delta of northern Canada. But finally, the first real hydrate samples were recovered indirectly through other ocean drilling program ones. We'll talk more about here in a second about some of the other ones. So let me seem to have, make sure, just pen. Yeah. Never used the pen, but apparently I must have. Okay, well, hopefully that's not too annoying. So, okay. So first off, gas hydrate stability conditions, as you know, probably one of the most important first aspects. Does anyone know Zoom well enough to know how I get rid of my pen marks I must have put on the screen? I'm open to suggestions. Sorry. Okay, I'm just going to push ahead. We'll deal with my little red lines. So hydrate stability conditions, this is an example of a permafrost condition somewhere like northern Alaska. We have temperature along the top of the axis, 0 degrees Celsius. We have depth in meters or pressure, increasing pressure. We have the methane hydrate stability boundary, and we have a geothermal gradient projected from the surface about -10 degrees Celsius to base of permafrost or the 0 degrees Celsius isotherm, and then a lower injection. So the zone in which hydrates have the potential of occurring extends from about 200 meters to 1 kilometer deep. So what's a very critical issue when you think about hydrates is always appreciating the pressure temperature field in which gas hydrates can occur. And one of the examples of this, of course, is throughout the Arctic in this type of situation. And this represents about 1/4 of the land mass of the world. And so when you study hydrates or talk about hydrates to others, it's very important to keep in context that about 1/4 of the land mass of the world is underlined by conditions in which the occurrence of gas is actually in solid form. So next. So I'm going to do one thing. I want to check something. So, okay. Okay. Sorry. Next, the hydrate stability diagram here, we've replaced the sediment column from a permafrost setting. We've moved to a marine environment. We have the base of the seafloor here at a depth of about 1,200 meters. It's the same geologic configuration relative to depth and pressure and temperature. We have the same methane hydrate stability curve. But as we know, at water depths greater than about 300 meters, 400 meters throughout the oceanic environments, even in equatorial regions, we have very low seabed temperatures, around 2 to 3 degrees Celsius, geothermal gradient projected to some depth below. So we have the zone of hydrate occurrences or potential stability of hydrates extending from some depth in the water column from the seafloor and below. This of course explains areas where you see vents and seeps, of course, at hydrates, but also the potential of trapping even free gas below. So anywhere we have a water depth below about 400 meter depth, again, most of the world ocean basins, but particularly the continental margins, are underlined by stability conditions in which gas hydrates have the potential of occurring. So the most important thing when we study petroleum systems of gas hydrates and systems is this occurrence of the stability field and others relative to that setting. Hydrate reservoir conditions and the nature of hydrates. It's very important when you study hydrates is that you often get, almost distracted by the aspect of the volumetric potential of gas hydrates. And one of the things we do in resource evaluations, we use simple concepts often to depict one resource relative to another. And we often use concepts like a resource pyramid. And in the pyramid concept, basically to compare and contrast resources is based on two aspects. One is the volume of a certain resource within a resource pyramid depicts the volume of that resource in nature. The other thing in general, from the top of the pyramid down, the resource becomes more difficult to produce. So at the top of this diagram, we have conventional resources, gas resources produced since the 1860s, late 1800s in most of the world. However, what we note is even though they're relatively easy to produce, they're the smallest in total volume. The next, as we move down through the resource pyramid, we see increasing volumetrics of each resource, but increasing difficulties. So we see today things like shale gas and coal bed methane and deep gas reservoirs produced since the 1990s and forward. But at the base of this resource pyramid, this is a total in place volume of gas, is some of the estimates of gas hydrates. So gas hydrates make up a very large total in place volume of gas relative to other conventional and unconventional resources. But it's very important aspect to take a look at what is included or the nature of these hydrate occurrences in the lower part of this diagram. Many years ago, myself and Ray Boswell with US Department of Energy generated a diagram. It was a gas hydrate resource pyramid. What we determined, we suggested at that time that the top of the pyramid, what are the most producible hydrate resources, we'll explain that and talk about a little bit, is hydrate and sand reservoirs, particularly in Arctic environments. More for technical reasons and accessibility reasons, marine hydrates fall below but are much larger within sand reservoirs. But the base of the pyramid is a very critical point, is that most of the gas associated with hydrates are actually disseminated in shales and fine-grained sediments at very low concentrations. So when people ask different questions about the producibility of gas hydrates or the resource potential, it's really important to put into context of what type of hydrate they're talking about. Are they talking about hydrates that are in fine sand reservoirs and sand reservoirs, or are they talking about very low concentration of hydrates in muds and shales? To put that a little bit more in context, to look at the hydrate pyramid or resource pyramid in a little bit more detail. Same diagram, we have the base of the pyramid made up of muds, what contain hydrates at very low saturation. As we move up the pyramid, we start seeing fracture-dominated hydrates. Many people, when they first come to gas hydrates, they've seen pictures like this. This is an image from the seafloor of a gas mound with hydrate outcropping at the seafloor. And when you take this to a resource manager and he says, oh, this is my resource, they quickly ask questions. How do you produce your resource and how do you control it and others? But as we move up the pyramid, we basically start moving into hydrates and sand reservoirs. So that's a very critical aspect that most of the world focuses today on resources that are relatively deeply buried below the seafloor, and it's hydrates occupying porous media and sands. So it's a very important concept that we're not necessarily, most groups are not focusing on shallow hydrates or subsea floor hydrates and others as shown here. So the next two slides, I want to talk about now the toolbox. What we know about gas hydrates is mainly come from a series of scientific and industrial drilling programs. And what we show here is both a map and the next one a timeline that are linked. Keep in mind, this map in 1995 would have been empty. So we would have no dedicated hydrate drilling programs. All occurred from 1995 forward, and most in the last 10 to 15 years. The first drilling projects for gas hydrates were those of the Ocean Drilling Program, like 164, and also 204 and 311 of ODP and IODP. These are science-based projects in which you're trying to characterize the currents of gas hydrates based on their geologic controls. These, again, very critical. They're science, not necessarily focused on resources. They focus more on issues like climate change and larger issues like plate tectonics and evolution of the Earth itself. From those projects, they developed the foundation where we developed a series of other projects. On the North Slope of Alaska, since the early 1980s, we've been conducting research on gas hydrates, their geologic conditions and controls. And we also have 3 production testing related programs that we'll talk about later. The first one is the Mount Elbert project with BP. The ConocoPhillips project was called the Ignik-Sakumi project. And there will be a test later on what Ignik-Sakumi means. So, and then humor's bad thing sometimes. And then finally, an ongoing testing effort, or at least the planning of the next phase, is it with JOGMEC, with the National Oil Company of Japan, Department of Energy, and JOGMEC listed twice, but it should be USGS there. So I apologize, that's a typing error on my part. The other significant marine gas hydrate project in the US before we move over to the other side of the globe includes those in the Gulf of Mexico. We had a joint industry project led by Chevron for a number of years. This project now has been led for the last 3 years by the University of Texas. So these are drilling and coring projects, not related to production testing, so the science. Hydrates really begin in the Arctic as a research issue with a MALIC program with 2 dedicated drilling geoscience program and a production testing program, 2007, 2008, again with partners like JOGMEC and the USGS. So strong international cooperation, Arctic project with groups like JOGMEC taking information on hydrates back to themselves in the area in Japan. In the Nankai Trough, what we see is 2 drilling programs. We see 2 production testing programs we'll talk more about. And finally, what we also see is the very significant projects also in China. We have 6 geoscience projects over the last 5 years and 3 production testing projects on the North Slope of the South China Sea. We also see a geoscience project coring hydrates in the near seafloor by MITI in the Sea of Japan. We also see 2 drilling programs offshore Korea in the Yulong Basin gas hydrate program, and also one of the projects we work extensively in of 2 drilling programs offshore of India, again in 2006 and 2016 are geoscience projects. For our discussion today, we're going to focus on production testing. What are the projects highlighted in red? For the sake of time, I'm going to move kind of quickly. I see I'm talking too slowly or too fast or too many slides. Is that this project or this diagram is directly linked to the map. So taken the act in northern Canada and also in northern Alaska, and the circles depicted in each one of these are geoscience projects, and these are squares. The squares are related to testing. So the distinction is geoscience versus production testing focuses. We see the long-lived projects now in China, but particularly the leadership that Japan has represented since 2000, really back to about 1995, for the series of drilling projects and production testing efforts. And our work in the Gulf of Mexico, mainly geoscience. So I'll go on from that, but it's important to see the evolution of each of these projects, one to the other. Gas hydrate production considerations. So this is more of a review again. We have a hydrate stability diagram. We have a hydrate reservoir within the methane hydrate stability field. So we have a solid form of gas hydrate and water and gas in form of hydrates. How do you produce those? How do you actually produce gas to the surface? One of the concepts and simplest one is lower the pressure. Lower the pressure or depressurization basically means a conventional well. This is basically the concept of how a conventional well works. The next aspect is trying to heat the reservoir itself, where you're trying to move that reservoir outside the stability boundary. The other concept is inhibitor injection, such as methanol, salts, and others, but also related to that is chemical exchange. I think many people have heard, we'll talk a little bit about CO2 exchange. That is injecting CO2 into a methane hydrate reservoir, displacing the methane because of the fit of the gas molecule, of the CO2 gas molecule in the cage structure, what kicks out the methane and sequesters the CO2. So these are the different methods. Most of the world today is focusing on one concept, and these are the concepts of looking at depressurization. So what's important, much like we talked about the drilling program and that being our toolbox of our information, the next thing is talking about the production testing programs that have been conducted. There have been few in nature. North Slope of Alaska, as we've already mentioned, and also northern Canada in these two examples, offshore in the Nankai Trough for the first marine test in 2013, and 3 additional tests in the South China Sea. One of the things you notice in this is time, this is the production rates, both based on gas at different units of values, is the short duration of these tests. These tests, for mostly a reason of just operational design, are either in deep marine environments or high Arctic environments where the tests were limited in duration because of the complexity of the work area. For example, on the North Slope of Alaska and the Mackenzie Delta is that you had to work from an ice pad when it was seasonal, so you could only test the well during the winter season, and your ice pad would melt. You would have to end your testing operation. So many of the tests are only on the order of 10, 20, 25 to 30 days, 60 days maximum. And these are some of the test examples we look. So one of the most important things about our understanding of gas hydrates is our appreciation of the fact that the testing information leading to our understanding of productivity of hydrates have only been a series of short-term tests. Most of these tests have been conducted for the reason to calibrate production models. So this is a very important concept. We have had limited testing, but the testing were designed to be limited in nature, largely because of cost and control issues, but they were used to design and calibrate a number of production models to actually model hydrate occurrence. I know this is something, particularly the group that is very familiar with. I had the chance to read a recent preprint of a paper looking at tough modeling and others. So again, the modeling aspect and the code calibration efforts are very important. Most recently in September, the Journal of Marine Petroleum Geology under Mark White's authorship published a very large code comparison study about gas hydrate modeling. So one of the most critical aspects, what really sets our entire discussion for the rest of the presentation today, is about the linkages between the limited production modeling and also the limited amount of actually testing itself. Field tests have been very limited in their nature, both in length, but also in the volume or rate of gas production. So these are in units of 60,000 and 940,000 cubic feet of gas per day. Just to put that in context, all of us in the world like to work in different units. In the US, we have a tendency still to work in cubic feet. I'm going to use cubic feet just as a reference point. Keep in mind that million is a poor well onshore in a low-cost area, 1 million standard cubic feet a day. You would hope that you would be achieving, for commercial purposes, more particularly in the onshore environment, around 4 million, and probably more in the 40 million. So what we've seen here is that the very short-term tests have yielded very limited gas rates. The long-term modeling or projecting into the future of long-term production rates suggests much higher rates. We have a disconnect. And this is really the state of our science right now relative to hydrates, is to understand that disconnect. So what I'm going to do now in this next part of the talk is just show very quickly a couple of the main reservoir sections from the Gulf of Mexico and Bay of Bengal as examples. These are more analog type things to consider for places like in the Black Sea, other places I believe in the Mediterranean. More so, I think along large passive margins also. I think many of these settings are probably more appropriate. In the Gulf of Mexico, we've had 2 drilling programs for geoscience, and most recently a coring program where we've worked with the University of Texas to do pressure coring. I'm only going to show a couple quick examples. And what was most important, in about 2010, we started to shift from the period of using BSRs, bottom simulating reflectors, as our main exploration tool, and moving on to the direct detection of gas hydrates, but particularly the reservoirs, in this case sand reservoirs, where the hydrates had the chance to occur at high saturations and also could be produced by depressurization. So this is a map of seismic evidence of gas hydrates ranging from BSRs in seismic evidence occurrence hydrates by BOEM. in others. So again, we had a series of drilling programs, both in 2005, 2019, and most recently, we went back to Green Canyon 2 years ago to do pressure coring operations. And what's most important by this discussion is that this was a site where we used different techniques to explore and characterize the site, then drill that. This is a seismic amplitude map of one of the hydrate bearing sand units, what are steeply dipping. This is the base of the stability field. These are the gases below the hydrates, gases below the hydrates. And these are actually directly imaged gas hydrates in a series of levee deposits in a channel section. And when you drill this as an example from the H well penetration, you get thick hydrate bearing sand sections or exhibited by high electrical resistivity acoustic velocities. So it's a very important aspect to be able to explore for hydrates, but also to visualize how hydrates and sand reservoirs occur. For most people, if I gave that figure to them, and didn't tell them were hydrates, those same physical responses are very similar to gas-bearing reservoirs and others, other than some of the aspects about the acoustic velocities. Offshore India, we've had 2 large drilling projects. Most recent drilling project in 2016 focused mostly on the Christian Godavari Basin. These are all published work, including a large publication just in October of last year with 47 papers on the results of the NGHP-02 expedition. Just to show this, the approach in this project, this is one of 4 areas we drilled. In this setting, we drilled a series of proximal channel levee deposits and distal fans. This is the section of wells. These are resistivity image. What's most important for our discussion is these blue horizons are hydrate-bearing sands in a series of distal fan deposits. And also we have thick channel levee deposits located more proximal. So again, what's the most important aspect is visualizing how hydrates occur in these different geologic areas with sand reservoirs. And this publication, again, is over 750 pages of reviewing of these different hydrate occurrences, all the way from the geoscience to the reservoir properties, including pressure coring with 125 pressure core deployments, plus all of the work done on production modeling of these potential hydrate occurrences. So now for the main focus is going quickly through just the results of a few of these key production testing programs, and then focus the last 10 minutes or so on reservoir properties. So I think that's the insight as scientists, what we really want to focus on. In China, we again have 6 geoscience projects, and we've had a combination of 3 now production testing programs, only 2 of which, 2017, 2018, are actually appear in the public domain. The hydrate occurrences in the South China Sea has been identified mainly from the Xinyu area. In this area and several other blocks, these are the Guangzhou Marine Geological Survey, the GMGS, if you want to know, is the organization that's been leading most of these efforts. These are the 6 geoscience expeditions in these different areas. But again, the production tests have focused mainly on the Xinyu area. The reservoir there is a little more unique because this is the base of the hydrate stability field. We have the high resistivity acoustic velocities. But one thing about these hydrate occurrences in the reservoir, oops, not sure where that's coming from. So just a normal pointer. Okay, are mostly fine-grained sediments with some coarse-grained components to the reservoirs themselves. So that's a very critical aspect of this reservoir. It's still what we would call sand or coarse-grained dominated with pore-filling hydrates. However, it does contain a significant amount of pore-filling hydrate in coarser-grained material. Apologize for my problems here. Let me do one thing. I'm going to open and close my PowerPoint, and hopefully I can make all those go away unless someone else knows what's my problem. Okay, what I'm going to do is share. Oops, sharing.
Doctor, you probably can do this from the control panel, I think, on the left side.
Okay, what I want to do, thank you for that suggestion.
You're very welcome, doctor.
Yeah, it's just something I should be more aware of. I actually, one of the rare people I use with so much more, what do you call it? Excuse me. So I'm going to just slide through this real quickly back to where we were. I use much more Office products. So Zoom, don't hear this often. I don't use Zoom much. Okay, China, thank you. So in the China testing program of 2017-2019, they used a very large semi-submersible rig, and it was located in the in the Xinyu area. In the 2017 program, what lasted again these short duration tests, and this testing program it lasted approximately 60 days for the total production rate or volume of 309,000 cubic meters of gas. Again, I was going to use for comparison purposes, this would be 60,000 or 600,000 cubic feet of gas production per day, and this would be approximately 1 million. So in 2017, 2019, they returned to the same reservoir section with similar completion. The production rates were similar in nature, and these were the reported values based on the volume of gas being produced from the reservoirs. What's most important for our discussion is to go ahead and look at the nature of the reservoir. But before we do that, I wanted to talk a little bit more about going into the data in more detail. And we were able to collect the data from various websites about production rate per day or production volumes per day. So this is the actual plot of the real data for the cumulative production and also production rates. So it was again reported the highest output was 1.2 million in an average of 600,000 cubic feet of gas per day. But it turns out when you actually look at the data in detail, you'll see that most of the gas was produced in the first 5 to 10 days, and quickly the production rate dropped to about 100,000 cubic feet of gas per day for the next 40 some days. So anytime we're looking at production results, it's very important not to just look at peak rates or even average rates. It's looking at the characteristics through time. So what we're seeing is a very high initial rate, slowing and then some plateauing of the production rate. This is one of the longest tests that's been conducted. This is the 2017 test for length of time. To move on from that, what does the reservoir look like? And this is an important consideration because this is the bottom simulating reflector. This is the test site itself. So this is evidence of free gas would be below this, and we believe many of these reflectors are actually free gas and sand reservoir. But this is the tested hydrate reservoir directly above an apparent free gas accumulation. When we look at it even in greater detail, and this is some work I had the opportunity to do with Shui-Yu Wang from the Academy of Sciences, is that when we look at the reservoir in detail, this is the high resistivity nature of the hydrates, high acoustic velocities and saturation. The one thing we determined was the hydrate section, what was tested, also contained free gas. That is, conventional gas trapped in and below the hydrates itself. This was also a structure 2 gas hydrate occurrence in the sense that it had thermogenic hydrocarbons associated with it. As you know, probably 80–90% of all the hydrates in marine environments are from microbial sources and are only methane. But in the South China Sea, we see the hydrate occurrences what are here, what are commingling as a structure 2 is structure 1 hydrates, including free gas. The other aspect of this, that the production test what was conducted in China was actually conducted both in the hydrate and free gas leg. That's very important because when we look at the production test results, it's not a pure hydrate test. This might be a good way to produce higher volumes and rates, but you really don't know if the gas is coming from the free gas phase or the hydrate phase as you're producing it. So this is a difficult test to interpret the results, and it doesn't really add a whole lot of insight to how the hydrates themselves are responding. So when we look at both of the tests, both the 2017 test, you have to really look at the aspect that there's a free gas involvement in those tests. And that's very unclear in the literature what's been published so far on the China test. In Japan again has been a leader in gas hydrate research for many years. They've had 2 primary production tests again, in the Nankai Trough, we had peak production rates. We'll show it over a production period of only 1 week of production. About 700,000 was their peak production rate over that, or averaged across the 6 days of that test itself. So again, 700,000 cubic feet of gas per day, averaged across the 6 days for cumulative production. And then they had 2 additional testing programs at the same site. And we'll talk a little bit about the site here in a minute, but we had 2 wells. And the first well was produced for 12 days, produced about 102,000 per day on average, and then 24 days of 291,000. So in comparison, these rates are a little lower than what we saw in China, except for the first test back in 2013. For the sake of time, I'm going to move ahead and talk about the reservoir. The reservoir itself is very interesting. They completed across a very complex series of reservoirs, included both turbidite sands, or thinly bedded sands, high resistivity, and also more channelized type fan deposits. And also within this section, there are significantly thick water-bearing horizons, what will actually flow. So one of the concepts are when you draw down the pressure on the reservoir, you want to be able to focus on the hydrate and the broad drawing the pressure in that reservoir. If you have a very thick or present water-bearing sand horizons, you'll actually have to pump down the pressure on those. So one of the things we see, particularly in the second Japanese test, is that the completion in the water-bearing zones gave them difficulties in the sense they had a difficult time pumping down or lowering the reservoir pressure on the hydrate section because of the high transmissivity of the water-bearing sections themselves. To look at that test, the first test for marine gas hydrate test was shown here back in 2013. The red curve is the actual production rate. And as we've seen, about 700,000 cubic foot per day on average, but the individual rates of about 20 when you look at this trend popping up on this scale through here. What's nice about this test, this is pretty stabilized. Oftentimes you see in test what we'll show here in another example from the Nankai Trough, what is much less stable than this flow period. Again, very short period of time. The test sites itself, this is the 2013 test site, very closely located in the same reservoir sections, just juxtaposed was the 2017 test itself, just to zoom up to show that. And I didn't really highlight, but when you look in the papers themselves, they're not just test wells. They also drilled geoscience wells for coring, LWD, and also for monitoring with the instrumented the holes. Papers by Koji Yamamoto goes through very extensively what have been published on the production results, particularly looking at the results at the observation wells where they're trying to characterize the production itself. When we look at the first well being tested in 2017, we see similar curve, red curves, kind of similar production rates, a little lower in this case in others, but sustained with a different completion. If we had more time, we'd talk about the different types of completions used for the borehole itself. This was the second test well. It actually produced at slightly higher rates, but they had many different complexities. And what's interesting to look at this is the green curve. Every time we lower the pressure of the reservoir, we get increasing water production rates, increasing gas production rates. So we're seeing direct response of the pressure response of the reservoirs themselves. And many of these things are disruptions. These are engineering disruptions, problems with disconnect, changing pumps, sand production, and many other issues. So the spiky nature to it is part of a natural reaction of the reservoir, but a lot of this is also mechanical. So, but what's most important as a scientist, we see below the hydrate stability field, we see lowering of pressure, the production of gas from the hydrate phase, and the production of water increasing with each pressure lowering. And we're going to look at another site in Alaska here shortly, the same type of response. What's very important to finish off this discussion about Japan, when we look at the completion interval, we have the hydrate-bearing reservoirs shown here in the bright green, but the purple are actually water-bearing reservoirs. So one of the factors what's controlling the production rate is the ability to draw pressure down on the reservoir. The fact that the high flowing rate of water made it difficult by the pump designs the design of the well to actually depressurize, to put much driving force into the reservoir to dissociate the hydrates. In Alaska, and this is where we're going to onshore environment, permafrost setting, we're going to focus a little bit more on petrophysics. In our projects on the North Slope of Alaska, we have the BP project, Mount Elbert, geoscience-based ConocoPhillips testing project, CO2 displacement, and finally Alaska North Slope, extended gas hydrate production testing, what we're involved with at this time. The Mount Elbert drill site was a fault imaged, seismic imaged gas hydrate occurrence on a large fault block. When drilled, we had 2 thick sand reservoir sections for that well. What we were able to image, this was an approach to actually characterize the occurrence of hydrates in the sense of an exploration model. We also did MDT pressure testing in the reservoir. We also had extensive nuclear magnetic resonance logging to characterize the reservoir properties. When we combine those 2 pieces of information, both the nuclear magnetic resonance logging shown here on the left, and we combine it with production testing in the form of wireline pressure testing, we're able to actually evaluate the porosity and permeability of the reservoir. And this is one of the first times we're actually able to measure the effective permeability of the reservoir. But we were determined at this time to range from about 0.1 to 1 millidarcy. And we saw that consistently. The NMR data and the MDT testing data, pressure data, showed very similar effects or results of low effective permeability as the reservoirs, what we in turn used in our production models themselves. This insight, along with some additional insight from acoustic well logs, these are sonic well logs, so this is a cross plot. What Young Lee and I did a number of years ago, we took shear velocities from acoustic logs, P waves, and we did different models based on the effective medium theory for the occurrence of hydrates in porous media. And this was work what groups out of Stanford started in the 1980s. They said, does the hydrate actually occur cementing boundaries, coating grains, or do they occur within the porous media, or do they participate as a part of the loaded or the matrix loading or the load of the system itself? So we took the log data from 3 wells in Alaska in sand reservoirs and plotted those. And this is the model derived for the cementation model. This is the model derived for pore filling hydrates. And it turned out that most of the hydrates appear to occur in bulk pore volumes. They occurred as pore filling material. That's very important because what that tells you, along with the NMR MDT data, where we were seeing some evidence of effective permeability, still very low, but with this information, we're saying this appears to be mostly a water wet system where the hydrates occur in the bulk pore volume. So that's when we developed the first kind of hydrate reservoir model, where this shows what well logs, logging scientists like to use. This is all the solid matrix. This is the porosity. The porosity is made up of bound water, free water, and gas hydrate. So I would propose to you with this work, along with the MDT and the NMR work, that we concluded that hydrates were mainly occurring in as bulk pore water, participating often in the load-bearing part of the system, but there were also in water wet systems, that the grains are actually water wet, so the hydrates was more in this configuration. So this pathway also gave you the place of the effective permeability. So this is a very important discovery. It's very important when we think of the productivity of hydrates as an engineer, considering the fact that we have apparent effective permeability in the evidence of both acoustic log data and also the NMR and MDT data gives you some insight to why there is effective permeability. To go on with developing this reservoir model a little bit more completely, we'll look at the Ignik-Sakumi test on the North Slope of Alaska. This again was a CO2 displacement test. In this test, we drilled a well into a thick gas hydrate occurrence, shown here, high resistivity, completed the well across this section. We perforated the well after setting casing. We set sand screens. We injected a mixture of CO2 and nitrogen, and then flowed back that well after a period of soak. Again, this was a attempt by ConocoPhillips to look at the displacement of hydrates, where the CO2 molecule preferentially fits better in a structure 1 hydrates and would kick out the methane and be produced, as shown here, and sequester the CO2. to show the results of that effort. It's a very complex diagram. It would take considerable time, but the most important thing, what we're seeing, this is the pressure, the bottom hole pressure of the reservoir being pulled down by pumps. And what we cross here, this is a imagery of the methane hydrate stability boundary. So when the pressure drops below the boundary, we would expect the in situ hydrate to dissociate. When we actually cross the lower boundary, we would expect it to be the conditions where pure CO2 hydrate dissociate. So everything in the first part of this test, we've injected the gas into the reservoir, allowed it to soak, then we flowed the well back. Initially, we wanted to do a test analysis to see how much CO2 we got back. So we rode this test, this part of the test for these first 12 to 14 days. We actually ran it above hydrate equilibrium pressures, above methane pressures. And then only for the last 25 days, we drew the pressure below hydrate equilibrium. So what's important for the CO2 test, we injected, we expected a reaction, and then we closed the test. That is, we tried to produce everything out of the reservoir to see what had actually happened during the soaking phase. And what we're able to see, again, pressure, these are different disruptions in the operational program, much like we saw in the offshore of Japan. And what we actually saw in the flowback, we're able to recover about 45% of the CO2 we injected in the reservoir. We do feel, and this is during the period of time where we've not gone below hydrate equilibrium for CO2 hydrate. So what we feel is that there is a 60% CO2 displacement that took place. It's much more complex than these simple descriptions. I would advise reading the papers. That we see that the exchange process took place. However, we determined at this time as a commercial process based on rates and others, it was still a pretty challenging test to justify moving forward additional research in this area. But one thing, and this is probably one of the most interesting diagrams, and I know we're kind of running a little late here, but I wanted to show very quickly the drawdown pressure. So I wanted to look at this period of time. We're going to basically look at this as a depressurization test now, that we're going to drop the pressure of the reservoir below the methane hydrate equilibrium conditions. And I really enjoy this test because what it does, and I'll bring up the additional information, this is the reservoir in depth. This is the DTS. This is the temperature of the formation itself right at the completion. These are the pressures being drawn down on the well, the red line, and these are production rates shown here in the black curve. So what happens is as we lower the pressure, remember we go below hydrate equilibrium, we start producing gas hydrates. So that's the sand, the gas coming from the sand reservoirs we've seen producing gas. What we see is every time we lower the pressure of the reservoir gets cooler. That's, of course, the endothermic reaction of hydrate dissociation. So it's very interesting. Even if just several psi drop in pressure, we get increasing production rate and temperature increase. So it's one of the best images I know to help you visualize a gas hydrate reservoir during production. And what I mean by that is that the energy in is depressurization, and the energy out includes the gas being produced as a component, but also the endothermic reaction. This diagram gives you insight to what a producing hydrate well will look like, particularly over a long period of time. And then the fact that you're going to have to balance depressurization with rate of gas production relative to the thermal effect. So this short-term duration test, even though very short, I think gives one of the best imageries of what hydrate production will look like. Finally, one of the problems is in a test like this, you start seeing the problems associated with the endothermic reaction. Endothermic reaction, the cooling of the reservoir itself, is our, quote, enemy when we're trying to produce hydrates, because the reservoir, as we're lowering the pressure, energy in, is trying to cool itself. So if we put this into a hydrate stability field condition, this is the starting of our reservoir, we're lowering the pressure on the reservoir. The minute we start dissociating hydrates, we see the reservoir temperature going towards ice point. So when we see that in a permafrost environment where we have a very minimum margin to work with of only 4 to 5 degrees Celsius before we get to the ice point, it's very important. Many of our marine hydrate reservoirs are at 20, 25 plus degrees Celsius. So you have more of a margin to work with. So this is really important when we start comparing data from marine and permafrost environments, is to appreciate this difference. So also with appreciation of our timing, I'm going to go through a couple of slides kind of quickly. To address this long-term production testing issue associated with hydrates and the fact of these short-term duration tests is JOGMEC, National Oil Company of Japan, USGS, and DOE have entered into a multi-well drilling program. We have already drilled the first well in the production testing plan to confirm the test site. It's called the Strat test well. We will be drilling middle of next year 2 production test wells and geodata wells, and they will be extensively instrumented to evaluate production. And we're planning on conducting a 1 to 2 year long production test. Again, this is an area on the North Slope of Alaska, very near the Ignik-Sakumi well. And on the integration test, I just want to finish here in the next 4 or 5 minutes in talking about what is the drive. As a petroleum engineer, what I'm most interested in is when I look at the reservoir, I have a series of equations. I have a series of relationships that are based on permeability and heat flow, of course. When I think of permeability, it's the issue of the ability to draw the pressure down the reservoir and how pressure transient will move across that formation. The next part is heat transfer. And what I mean by heat transfer, we know this reservoir is cooling. Most of our heat, of course, in this section where we're not adding any heat, is coming from the surrounding rock mass. So all of our equations, our stability programs, and others have this very simple concept of focusing on the impact of permeabilities, particularly effective permeabilities in others, inflow of fluids and waters from bounding rock units, and also the heat displacement itself. And hydrates can only be produced effectively if you hit some type of a balanced relationship between production rates, what controlled mainly by permeability, your pressure transient in the actual thermal heat flow in the reservoir. One of the best insights is, remember, we talked a lot about NMR and MDT testing. In the last 5 to 10 years, we've been focusing more on pressure coring. And some of the pressure coring results, including these are some examples from the Nankai Trough of recovered pressure cores. When they're covered to the surface, the hydrates are stable. You can conduct detailed analysis of the core under pressure conditions. And what we saw in these very early tests from about 8 years ago, that the actual effective permeabilities being predicted from the pressure cores were much higher than those predicted previously by MDT and NMR. We continued this same work into India back in 2016. And what we found from our pressure coring work in offshore India, and also combined it with other areas, including those in the Nankai. Keep in mind, these are the only 2 projects with extensive pressure coring operations and analysis. It's a technology that's only recently become mature. We see, again, effective permeabilities 10 to 100 millidarcies, much greater than our history of permeability measurements with MDT and NMR. And I'll probably save this kind of more for our discussion about the significance of that, but the most important significance is that the permeability, or particularly effective permeabilities of hydrate reservoirs, may be higher than we expect from this MDT and MR testing. So again, this is an evolutionary idea about how permeability, effective permeabilities work. And the reason this is important, just to show my last diagram, if we assume an effective permeability of about 10 millidarcies, we expect a production rate for this reservoir, what's offshore India, over 4 million standard cubic feet of gas per day. But if we would be using the lower permeability, we see around 400,000. So this is a major issue still about our lack of appreciation of the permeability conditions are. So in summary, first off, thank you for your time, but in summary, application of the petroleum system concept, we didn't really go into it, but that was kind of implied when we were looking at some of these reservoir settings, where we actually make great use of the concept of petroleum systems, where we look at the source of the hydrocarbons, the migration, the reservoir relationship to actually explore for gas hydrates. The global volume of gas and hydrates is not really, we feel, that important of an issue relative to resources. What's more important is hydrate volumes at a given range of basins and the individual well scale. And what we're really indicating is, the information on hydrates that we have. Hydrates in porous media, we have high volumes. You can establish depressurization across them. Recovery ratios should be high, and we can explain that a little bit more detail in additional discussions. However, hydrates are challenging in the sense that they're cold temperature. In my last slide, what I'll leave up for our discussion, basically leaves us with the challenges of gas hydrates. And the main challenges are that, to support gas hydrate modeling, keep in mind, we're not going to have 100 gas hydrate test wells tomorrow. Most of our work with test wells and others are going to focus on the acquisition of data to calibrate production models. It's a very important component. So the use of pressure core data, the use of NMR data and MDT, but what's even more important is the extended production test. We really need tests long enough to establish and identify the flow of gas from hydrate reservoirs over a long period of time instead of these short duration tests. The tests also, and they have all included this, but they need to maintain this and move even more effectively forward, is mechanical and environmental test. Every one of our tests are heavily instrumented wells to look at mechanical strength, subsidence issues, gas release at the surface. All of this is a critical aspect to understand the resource entirely. It's just not the volume of gas per unit time. It's also its impact, both of how the well and the reservoir changes would affect production, but also on the environment itself. And finally, we further developed the calibrated production models and others, particularly with mechanical components, and then demonstration. We really feel we're reaching the point of time that beyond these scientific tests, that we also need to start looking at demonstration tests, what would be more appealing to particularly industry partners, where we're looking at how to maximize production rates. It's a very important concept, again, when we look at the history of production testing, that most of the tests have been conducted to calibrate models. They've been constrained tests by design. Someday along the way, to really demonstrate the capabilities of producing gas from gas hydrates, you need to move beyond just the science and modeling aspect to actually look at larger scale depressurization tests. In some of these considerations we have underway for a second phase of the extended test on the North Slope of Alaska. So again, thank you for your time. And appreciate it. Any questions or however you want to proceed, I'm here. So
thank you very much, Doctor. It was a very informative and insightful presentation.
Thank you.
I would like to start by my question. I have read that the United States found some gas hydrate prospects in the Gulf of Mexico. But instead of marine sediments, United States prefers to conduct it as gas hydrate production trials in the Alaska permafrost.
Sure.
What is the main reason of this? Is it because of budgets?
Right. Yeah, when we look at, and one of the most critical things we think about gas hydrates, and this is very important when you start thinking about the energy resource potential of hydrates, it's not just the technology, it's also economics and cost, right? So the Arctic, where hydrates occur in deep marine environments, are two very expensive places to work. But relatively speaking, it's about a 10-to-1 cost between our wells onshore on the North Slope of Alaska and our wells in the deep marine environment. So our daily expenditure for the North Slope of Alaska for a test well to drill is about $50,000 US a day. So it's still a significant amount of money. But in the Gulf of Mexico, it can be easily $500,000 a day. So those are the impacts on us as a science program. We go to places where we optimize sciences. So what's of interest to us, we know there's differences between the two different reservoir settings, but the occurrence of the hydrate in the porous media, the mechanical nature of how the hydrates appear to be distributed in the permafrost and marine environments appears to be similar. The pressure temperature conditions, oddly enough, are pretty close. The pressure a little higher and a little different depending on where you're at in the marine environment. So we're using right now, because of cost, in enough similarities to use Arctic gas hydrate accumulations as an analog, for marine gas hydrate occurrences. And truthfully, and this is, one of those industry ways to say something, is that if you can't probably prove production from a permafrost setting, at least short term or to extended term, it's going to be very difficult to demonstrate it in a marine environment. So we think it's an important analog test, but eventually Keep in mind, most hydrates are in the marine environments, in sand reservoirs, in those settings and others. You do have to shift those focus. And most all of our partners don't have the Arctic. I mean, our partners are Korea, Japan, China, India, and we've worked with all of them in the Arctic, but we've also worked with all of them in their environment. It's a good question. It's a very important issue about how you decide to approach a scientific topic of where you go to maximize your results, hopefully.
Thank you very much, Doctor.